Welcome to homework.
So, once again, welcome to a new problem. We're still on the visible spectrum, a little bit of variation on diffraction, and this time we have visible light. It's a visible spectrum, so it means that you can actually see the light. The limits of the spectrum happen to be 430 nanometers and 680 nanometers. We have that, so the light is coming in, and obviously it's going to spread out because it's a spectrum, and all the way up until a screen on the opposite side. And this is the diffraction grading. This is the diffraction grading, and we want to find the number of rulings n. That's our goal. Find n, which is the number of rulings in this case, per millimeter of the grading. This is the grading that will spread out through an angle of 20 degrees. That's the angle we're dealing with. So we still have the condition for first order. This is the condition for first order, and it so happens that d sine theta equals to m lambda. Remember, m is the first order. Theta is the angle of diffraction. That's our theta. We know that lambda 1 is 430 and lambda 2 is 680. So assume the position of lambda 1 is at theta, and then the position of lambda 2 is at theta plus delta lambda, or is at theta plus delta theta. Obviously, the gap between these two angles is delta theta, and that delta theta happens to be 20 degrees. That's our delta theta. And we're going to use the two conditions. So if we jump onto the next page, we know that d sine theta equals to m lambda. And so d sine theta equals to m is 1, meaning it's first order, equals to lambda 1, and also d sine theta equals to, well, of course, the second angle is displaced at theta plus delta theta. That's lambda 2. If you go back, d is this gap. That's d. That's the width of the diffraction grading. So from the first equation, we see that sine theta is lambda 1 all over d. And so it follows that if that's sine theta, we can also get cosine theta. Cosine theta is radical 1 minus lambda 1 all over d. And the reason that's the case is because cosine theta is the same as radical 1 minus sine squared theta. How did we end up with that? There's a trigonometric condition that says that cosine squared theta plus sine squared theta equals to 1. So cosine squared theta equals to 1 minus sine squared theta. And cosine theta will then become plus minus, or rather plus minus sine 1 minus sine squared theta, because you're doing the radical. But we're only interested in the positive relationship, so we don't need the minus. And so cosine of theta equals to radical d squared minus lambda squared, lambda 1 squared, all over d. That's just a variation of this formula. And then we'll go ahead onto the next page, and we get to see that sine theta plus delta theta equals to lambda 2 over d. And the reason for that is that d sine theta plus delta theta is lambda 2. So we're using that, and so it follows that we can use identities. Remember, sine of a plus b is the same as sine a. Cosine b plus cosine a sine b, and therefore sine of theta plus delta theta, assuming theta is a and delta theta is b, becomes the same as sine of theta cosine of delta theta plus cosine of theta sine of delta theta equals to lambda 2 over d. Those are trigonometric identities. In the previous page, you can recall this is a special resolution that sine theta is lambda 1 over d. We did use that right here, just as we used it right here. It's the same thing. And so going back to this page, we see that sine of theta, which is lambda 1 over d, cosine delta theta plus cosine theta. If you go back, that's where we had cosine theta. We use it now. It's the same as radical d squared minus lambda squared, lambda 1 squared all over d. Sine of delta theta equals to lambda 2 all over d. And so we can multiply everything by d. You could see that times d. And then this one also times d, and this one times d. So we eliminate the width, and we have a simpler formula. On the next page, we see that lambda 1 cosine delta theta plus radical d squared minus lambda 1 squared sine of delta theta equals to lambda 2. As you can recall, we're going to solve for d and use that to find the number of rulings. And so radical d squared lambda 1 squared sine delta theta equals to lambda 2 minus lambda 1 cosine delta theta. So we subtracted this on both sides. And so we can see that radical d squared minus lambda 1 squared equals to lambda 2 minus lambda 1 cosine delta theta. We're dividing all of that by sine theta, sine delta theta. So sine delta theta, we divided both sides. And so in the next page, we end up with, if you go back, we can square both sides to eliminate the radical sign. And whenever you do that, you end up with d squared lambda 1 squared equals to lambda 2 minus lambda 1 cosine delta theta squared all over sine squared delta theta. So d squared has to be lambda 2 minus lambda 1 cosine delta theta squared all over sine squared delta theta plus lambda 1 squared. This one goes to the other side because it becomes a plus when you subtract it. So in the next page, D is radical lambda 2 minus lambda 1 cosine delta theta squared plus lambda 1 sine delta theta squared all over sine squared delta theta. So all we did is to combine this by multiplying the numerator and the denominator by sine squared delta theta. And so the next portion is to plug in the specific numbers. So we still have the radical, and lambda 2 is 680 nanometers minus lambda 1 is 430 nanometers times cosine delta theta is 20. We square all of that plus 430 nanometers. Sine of 20 again, we square that. Then we divide everything by, and all this is under the radical, so we divide everything by sine of 20 degrees squared. It makes sense to extend this to make sure that we see what happens. So these are, we want to have a radical there. This is a radical. And so in the next page, we have D equals to 914 nanometers, if you simplify that. And we can change that to millimeters. So this is times 10 to the negative 6 millimeters per nanometers. And so D is 914 times 10 to the negative 6 millimeters. And so N, which is the number of rulings, is a reciprocal of D, since we're saying N is the initial requirement of this problem. So we're looking at the number of rulings per millimeter. So going back, we simplify this fraction, number of rulings per millimeter, is N, which is a reciprocal of D. And so here we have 1 over 914 times 10 to the negative 6 millimeters. And that's going to give us the number of rulings per millimeter, which is N. And so that's 1094 rulings per millimeter. So once again, we had a problem. We're given delta theta, which is the angle between lambda 1 and lambda 2. Our goal is to find the number of rulings per millimeter. D sine theta equals to m lambda for first order. That helps us solve for sine theta. And then using the identity cosine squared theta, sine squared theta, we're able to solve for cosine theta. Using another identity, we get lambda 2 over D and simplify it. So in the next part, we go through algebraic simplifications in order to isolate D. At this point, we have D squared, but eventually isolate that to D, which is the width of the grating. And so finally, we get the reciprocal of D, which is the number of rulings. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.